Okay, then chapter 5, magnetism and matter. This is part 2 of this chapter actually. So this is part 2. I will start from where I left off yesterday. That is an example. I have completed magnetization and magnetic intensity. This topic I have completed. Now I will start from this example, which I did not do yesterday. Example 5.5. A solenoid has a core of a material with a relative permeability 400. The solenoid has a core of a material which is having relative permeability to be 400. Relative permeability meaning the 1 plus chi value, or mu r value, not 1 plus chi. It is mu r value, which is equals to 1 plus chi actually, where chi is the susceptibility. The windings of the solenoid are insulated from core and carry a current of 2 ampere. If the number of turns is 1000 per meter, calculate A, the magnetic intensity, B, magnetization, C, which is magnetic field, and D, the magnetic current IM. Okay, they are asking how to calculate. They gave the number of turns per unit length, that is 1000. They gave the current, they gave the relative permeability, that is mu r value. To find out H value, we have okay, let's see first, I guess. The magnetic intensity is dependent on the material of the core, and is which is equals to H equals Ni, which is 1000 into 2, which is 2000 ampere per meter, or 2 into 10 power 3 ampere per meter. The magnetic field B is given by B equals mu r mu naught H, and mu r, which is 400, mu naught is 4 pi into 10 power minus 7 into magnetic intensity is 2 into 10 power 3, which will get as approximately 1 Tesla. Magnetization is given by magnetization, which is equals to B minus mu naught times H whole by mu naught, which will get approximately to be around 8 into 10 power 5 ampere per meter. Now the magnetizing current IM is the additional current that needs to be passed through the windings of the solenoid in absence of the core, which would give a B value as in presence of the core. Okay, they are saying this topic was, I believe, not introduced here. So they are saying this magnetizing current is the current if there is a core, there is an amplification in the magnetic field produced. If there was no core, there would be less magnetic field than when there was a core. So if without a core, what is the amount of current, what is the amount of current we should increase so that we get the same amount of magnetic field? That is 1 Tesla here. 1 Tesla. The magnetizing current, the additional current that needs to be passed through the windings of the solenoid in absence of the core, which would give a B value as in presence of the core. Thus, mu Rn I plus Im using 2 ampere 1 Tesla, we will get Im to be around 794 ampere. That is a very large amount of current compared to our 2 ampere here. Wait, yes, 2 ampere here. Which really says that it's a really important to have our current. This formula we got it by B, which is equals to mu naught Ni. This formula we used and we got this value. And I we wrote it as I net, which is equals to I plus In. Now let's go to the next main topic, magnetic properties of materials. The discussion in the previous section helps us to classify materials as diamagnetic, paramagnetic, or ferromagnetic in terms of susceptibility chi. A material is diamagnetic if chi is negative. I'm not sure if it is chi. Let's just. What is the term that denotes magnetic susceptibility and how to pronounce it? Yeah, it is indeed chi. It is indeed chi. So classify materials as diamagnetic, paramagnetic, or ferromagnetic in terms of susceptibility chi. A material is diamagnetic if chi is negative, paramagnetic if chi is positive and small, and ferromagnetic if chi is large and positive. A glance at table 5.2 gives one a better feel for these materials. Here, epsilon is a small positive number introduced to quantify paramagnetic materials. Next, we describe these materials in some detail. Okay, they gave a table here. It gives us better feeling for these materials seems. And epsilon is here the E value. This E, they are saying it's a small positive number and it is introduced to quantify paramagnetic materials. Okay, then diamagnetic chi is between -1 to 0. Permeability, relative permeability, which is 1 plus chi, is between 0 to 1, and mu is smaller than mu naught. Permeability is less than mu naught. That is the reason mu r, which is not greater than 1. Paramagnetic chi is between 0, chi, and epsilon. It is mu r, which is 1 plus epsilon and 1 between. And here, since it is greater than 1, mu, the permeability of the medium, is greater than permeability of the air. Ferromagnetic here, chi is greater than 1, mu r is greater than 1, and mu is greater than mu naught. Figure 5.7, this shows behavior of magnetic field lines near a diamagnetic, first one diamagnetic where only one line is passing, and paramagnetic substance. Here it seems like the magnetic fields are avoiding the substance altogether. That means the permeability of the substance is less. And here all the magnetic field lines are getting accumulated here, getting bending inside. Now let's start with the next main topic, that is diamagnetism. Next main subtopic, that is diamagnetism. Diamagnetic substances are those substances which have tendency to move from stronger to weaker part of the external magnetic field. Okay, meaning they will get repelled, as the stronger part will be in the north pole. As more number of field lines will be going from there, it will get repelled because north pole is generated in the diamagnetic substances, meaning they will go to the weaker part of the field. In other words, unlike the way a magnet attracts metal like iron, it would repel a diamagnetic substance. But it is okay to remember that substances have tendency to move from stronger to weaker part of the external magnetic field. Figure 5.7a, that is diamagnetic, shows a bar of diamagnetic material placed in an external magnetic field. This is an external magnetic field. This is a bar of diamagnetic material. The field lines are repelled or expelled in the field. Inside the material is reduced. Basically, the field is getting repelled here, and the magnetic field lines inside the material is reduced. In most cases, this reduction is slight, very slight reduction, being 1 part in 10 power 5. When placed in non-uniform magnetic field, the bar will tend to move from high to low field. That is meaning it is getting repelled. The simplest explanation for diamagnetism is as follows. Electrons in an orbiting around nucleus possess orbital angular momentum. Okay, basically electrons in the atom are orbiting around the nucleus. This is an electron, a charge moving, so this will create an orbital angular momentum. These orbiting electrons are equivalent to current carrying loop and thus possess orbital magnetic moment. This is kind of like a current carrying loop, so they possess orbital magnetic moment. And diamagnetic substances are the ones in which resultant magnetic moment in an atom is zero. Where diamagnetic substances, these are ones in which resultant magnetic moment in an atom is zero. When magnetic field is applied, those electrons have orbital magnetic moment in the same direction shown down, and those in the opposite direction speed up. Basically, they're saying that diamagnetic substances are the ones in which resultant magnetic moment in an atom is zero, because the electrons will get paired, due to which then resultant magnetic moment will be zero. But when that is when no magnetic field is applied, but when a magnetic field is applied, the electrons having orbital magnetic moment in the same direction, they slow down, and those in the opposite direction speed up. This happens due to induced current in accordance with Lenz's law, which you study in chapter 6. Thus, the substance develops a net magnetic moment in direction opposite to that of applied field, and hence repulsion. Let's read that again. They're saying that normally the net magnetic moment will be zero, but when a magnetic moment is there, magnetic field is applied. When magnetic field is applied, then the magnetic moment in the same direction of the magnetic field, those will slow down and the others will speed up. This happened due to induced current in accordance with Lenz's law. Okay, then. But just in case, let's see more about it. Diamagnetic substances, each atom has zero net magnetic moment. All tiny magnetic fields from electrons cancel out. No unpaired electrons. All electron orbits and spins are paired. Example, bismuth, copper, gold, water, and zinc. So in absence of any external field, they show no magnetism. But in case of a magnetic field is applied, even though diamagnetic atoms have no net magnetic moment, they still respond when you apply an external magnetic field. This response is temporary and very weak but real. Those electrons having orbital magnetic moment in the same direction slow down. Electrons orbiting the nucleus, tiny loops of current, electrons in an atom move in orbits. These orbits are like tiny current loops. A current loop produces a magnetic moment which is I into A. When you apply an external magnetic field, that is according to Lenz's law, the system resists the charge, resists the change. Okay, when you apply external magnetic field, the system is resisting the change. The magnetic field tries to induce a current in the electron's orbit to oppose the change. This is Faraday's law in the atomic scale. Induced magnetic moment will oppose the applied magnetic field. Electrons already orbiting in the same direction as applied field feel a braking effect. They slow down, their magnetic moment reduces. Electrons orbiting opposite to the applied field speed up, their magnetic moment increases. Net result, all these changes add up to create a net magnetic moment that opposes the external field. Why does this lead to repulsion? Since the induced magnetization is in opposite direction, the substance pushes against the external magnetic field. As a result, diamagnetic materials are weakly repelled by magnetic fields. But I am not sure why the electrons speed up. When you apply a magnetic field, adjusting in electron speeds is due to I not get that part. And let's see this first. Electrons are orbiting like tiny current loops. An orbiting electron is essentially a moving charge, so it acts like a current loop. This loop generates a magnetic moment. When we apply a magnetic field, a changing magnetic field, or even, did they mention a changing magnetic field? The simplest explanation for diamagnetism: when placed in a non-uniform magnetic field. So meaning there is a change in the magnetic flux. Electrons are orbiting like tiny current loops. An orbiting electron is essentially a moving charge, so it acts like a current loop. This loop generates a magnetic moment. When we apply an external magnetic field, be a changing magnetic field or even switching or a constant one, induces electric field according to Faraday's law, which is partial, like this is displacement. Induced electric field acts on the orbiting electrons, causing a change in their speed, either speeding up or slowing down depending on the direction of motion relative to the field. So why does the speed change? Because of Lorentz force. Is this only for a non-uniform? So it's just if it is magnetic flux only. This induced current, so it is mostly possible when there is a change in flux and also temporarily seen for constant field. Changing magnetic flux, this main situation where Faraday's law applies, where change in magnetic field by change in time, which induces an electric field. The effect is this subtly alters their orbital motion, produces small induced magnetic moment opposing the field. The explanation here is more quantum mechanical modification of atomic energy levels. Great. Changing flux is strong and temporary. Why? So if I had to do give a summary, so when there is an external magnetic field applied on a material, on a diamagnetic material, there will be Lorentz force acting on moving electrons. But how is current induced? Or even an electric field? And one more, can a moving charge have only magnetic field or electric field? And only, no, or only magnetic field? The Lorentz force acts on the orbiting electrons. This force modifies the electron's orbital motion. As a result, there is a change in the magnetic moment of the atom, even though the atom had no net moment before. This change is what we call diamagnetism. The induced magnetic moment is opposite to the applied field. If the magnetic field is changing with time, then where there is a change in magnetic field with time is not zero, where magnetic field is not constant, then this symbol, whatever it is, the inverse triangle times or cross product with basically negative of the change in magnetic field per change in time, which gives us an electric field. This electric field accelerates electron which change their orbital fields. But it is saying a magnetic field is induced in that region, but how so? Constant magnetic field. Okay. When there is a Lorentz force acting on an atom, then basically the orbits which which were in a way, in an optimal way, to cancel out net magnetic moment, will get altered or shifted so that the net magnetic moment is non-zero. But how can we say that actually, and I have an explanation how we can say that, like it's always in repulsive in nature. I believe it is, let's see. And this magnetic moment is repulsive, is in nature because maybe the shifting of the electron orbitals, electron orbits, is only in one direction due to a magnetic field. Is this correct for constant magnetic field and static? When a constant magnetic field is applied, the electrons are moving charges and they experience the Lorentz force. This force modifies the path, the velocity of electrons depending on their original direction of motion. Results orbits slightly shift or become faster, slower, depending on whether their magnetic moment is aligned or anti-aligned with applied field. This induced magnetic moment is always in the opposite direction, repelled by the external field. Direction of the orbit changes in such a way that magnetic moment opposes the applied magnetic field. But how can this magnetic force make orbitals faster or slower? Because I saw in the before chapter that magnetic force cannot, for a constant and static field, let's be more specific, magnetic field the there should be no speeding up of the electrons due to only magnetic force, as magnetic force does not increase momentum but only change direction. And Lenz's law is defining, actually my definition of Lenz's law is basically the way of defining why we need work done to apply a continuous change in flux so that the total energy is conserved. Okay, that's better. How can we induce current, say for our before example, before case, actually not example, considering a single atom in a varying magnetic field is current induced by speeding up the electrons. or how is it actually induced? And before a single atom case, how can current or be induced actually for a conductor only via change in magnetic field as magnetic force does no work. Yeah, I understood that much, that induced electric fields do the work. But how so? How is an electric field induced? It is saying that Faraday's law, but if a changing magnetic field passes through an atom, the orbiting electrons feel the induced electric field. But how can an electric field be induced with only a change in magnetic field? It feels like I'm going around in circles and wasting my time, but it's better if I understand it. Same equation again and again. Changing, twist the geometry of space, you say? It seems this is above our level, so it is best to understand. So a changing magnetic, final understanding of this paragraph here is, so a changing magnetic flux or magnetic field due to Lorentz force and the electromagnetic induction alters the stable or alters the net zero magnetic moment of the atoms of the diamagnetic substance in such a way that the magnetic moments are arranged to create a repulsive force. As for how the magnetic moments arrange, I'll take care of it later. A changing magnetic field through Lorentz force and electromagnetic induction disturbs the normally net zero magnetic moment of atoms in diamagnetic substance, producing a net induced magnetic moment opposing the applied field, leading to repulsion. In case of paramagnetic substances, the net magnetic moment is not zero due to unpaired electrons, and these in the presence individual magnetic moments of atoms align due to an external magnetic field to create a, an attractive force instead. They contain atoms around with unpaired electron. These electrons contribute a net magnetic moment to each atom in the absence of an external magnetic field. These atomic magnets moments are randomly oriented due to thermal agitation. So the net magnetization is nearly zero. What happens when you apply a magnetic field? When you apply an external magnetic field, the magnetic moments tend to align partially to the same direction as the field. This alignment is not complete because thermal energy causes no random motion. Opposing alignment. This alignment is statistical. More dipoles along the field than against it. A net magnetization M in the same direction as the field. Activator behavior. So magnetization for diamagnetic materials is due to altering of orbits of electrons and for paramagnetic substances is alignment of individual magnetic dipoles. Can we say magnetization for diamagnetic substances is more complex than paramagnetic substances? Requirements: unpaired electron, no. Dipole exists before field, no. Induced only, yes. Permanent. As we are disturbing the field, maybe that is we are disturbing the normal net cancellation. Maybe that is the reason it is opposite to the field. The direction of the magnetic momentum is same as the field. Quantum explanation. Okay, fine. I did not clearly say paramagnetism is more simple, but fine. That was quite wrong. Let's go back to our traditional textbook. Diamagnetism. I'll start reading again. Diamagnetic substances are those which have tendency to move from stronger to weaker part of of the external magnetic field, which is the common ability. Common, basically describing the repulsive nature of diamagnetic substances. In other words, unlike magnet attracts metals like iron, it would repel a diamagnetic substance. Shows a bar of diamagnetic which does not allow the magnetic field lines. In most cases, the reduction is slight, being part in 10 power 1 in 10 power 5, and placed in non-uniform magnetic field, the bar will tend to move from high to low field. The simplest explanation for diamagnetism is as follows. Electrons in an orbit in an atom orbiting around nucleus possess orbital angular momentum, and these orbiting electrons are equivalent to current carrying loops and thus possess orbital magnetic moment. Diamagnetic substances are the ones in which resultant magnetic moment in an atom is zero. When magnetic field is applied, these electrons have orbital magnetic moment in the same direction as wait the electrons having orbital magnetic moment in the same direction as the magnetic field. These slow down due to attraction, and those in the opposite direction speed up. This happens due to induced current, and that is accordance with Lenz's law, which we'll study in electromagnetic induction chapter. Thus, substance develops a net magnetic moment in direction opposite to that of applied field, and hence repulsion. Some diamagnetic materials are bismuth, copper, lead, silicon, and nitrogen, that is at STP, standard temperature and pressure, water, sodium chloride. Diamagnetism is present in all substances. However, the effect is so weak in most cases that it gets shifted by other effects like paramagnetism, ferromagnetism, etc. The most Exotic diamagnetic materials are superconductors. These are metals cooled to very low temperature which exhibit both perfect conductivity and perfect diamagnetism. Here the field lines are completely expelled where chi equals -1 and nu r which is equal to 0 where relative permeability is 0. A superconductor repels a magnet and by Newton's third law is repelled by a magnet. The phenomenon of perfect diamagnetism in superconductor is called as the Meissner effect after the name of its discoverer. Superconducting magnets can be gainfully exploited in variety of situations. For example, running magnetically levitated super-fast trains. Okay, basically they're saying that superconductors, which are very like metals, which are cooled to very low degrees, very low Celsius, very low temperatures. These act like superconductors and they expel all magnetic field lines. They will perfectly repel a magnet and get perfectly repelled by a magnet, and this is called as the Meissner effect. Okay, I have a wish to know how that works. So let's see. How can diamagnetic substances repel magnetic field lines? Is it by is it due to the alignment of the magnetic moments which which is produced being repulsive in nature, blocking the entering magnetic fields the result is a net magnetization in opposite direction. Internal field counters the external field. Okay. Okay, they do enter the diameter creates a tiny opposing field that distorts. Is it actually, does it mean, does that mean magnetic field lines get distorted or and don't enter the substance or the internal opposing field created inside will be equal to the magnetic field lines which enter, and the magnetic field lines net magnetic field inside becomes 0. Here the induced magnetic fields completely cancel the external magnetic field inside the material. For okay, I have, how does that happen for superconductors, but I think it would be too complex for our level, but just I want to know, so let's ask. Superconductors which have zero resistance due to lack of collisions between electrons, they, how can they have not zero, how can they cancel, they cancel, how can they act as perfect diamagnets? Is it due to lack of energy in the electrons which will give the external field to completely alter the internal magnetic moments such that an opposing field created is very strong. Okay, then let's go back to the main subject. Let's go to paramagnetism, the next main subtopic. Paramagnetic substances are those which get weakly magnetized when placed in an external magnetic field. They have tendency to move from a region of weak magnetic field to strong magnetic fields. That is, they get weakly attracted to a magnet. They're saying paramagnetic substances are those get weakly magnetized when placed in an external magnetic field, and they are getting magnetized when placed in an external magnetic field, and they have tendency to move from region of weak magnetic field to strong magnetic field, where diamagnetic substances we saw go from strong magnetic field to weak magnetic field, which is due to repulsion. Here, due to attraction, they go from weak to strong magnetic field. They get weakly attracted to the magnet. The individual atoms or ions or molecules of a paramagnetic material possesses a permanent magnetic dipole moment of their own on account of the ceaseless random thermal motion of the atoms. No net magnetization is seen in the presence of an external field P naught, which is strong enough, and at low temperatures, the individual atomic dipole moment can be made to align and point in the same direction as B naught. Okay, due to thermal motion, random thermal motion of the atoms, there is no net magnetization seen. But in case of a external field B naught, which is strong enough and at low temperatures, the individual atomic dipole moment can be made to align and point in the same direction as B naught. Maybe they suggest low temperatures because the thermal motion which will be reduced at low temperatures, and which can at low temperatures we can align them more easily, I guess. 5.7b, this is the paramagnetic substance where it's allowing the magnetic field lines inside, or it's increasing the magnetic field inside basically. The individual atom dipole moment can be made to align and point in the same direction as B naught. Figure 5.7b shows a bar of paramagnetic material placed in an external field. The field lines get concentrated inside the material and the field inside is enhanced. In most cases, the enhancement is slight, being 1 part in 10 power 5. When placed in a non-uniform magnetic field, the bar will tend to move from weak field to strong. Okay, when placed in a non-uniform magnetic field, this bar will tend to move from weak to strong field attracted. Some paramagnetic materials are aluminum, sodium, calcium, oxygen, STP, and copper chloride. For a paramagnetic material, both chi and mu r depend not only on the material but also in a simple fashion on the sample temperature. As the field is increased or the temperature is lowered, the magnetization increases until it reaches a saturation value, at which point all the dipoles are perfectly aligned with the field. Okay, that seems simple. Now let's go to ferromagnetism. Ferromagnets, these are randomly oriented domains. Okay, introduce a new term here, domains and aligned domains. Ferromagnetic substances are those which get strongly magnetized when placed in an external magnetic field. They have strong tendency to move from a region of weak magnetic field to strong magnetic field, that is, they get strongly attracted to a magnet. The individual atoms or ions or molecules in a ferromagnetic material possess a dipole moment as in a paramagnetic material. However, They interact with one another in such a way that they spontaneously align themselves in common direction over a macroscopic volume called as domain. The explanation of this cooperative effect requires quantum mechanics and is beyond the scope of this textbook. That is, each domain has a net magnetization. Okay, let's read that paragraph again. They're saying there are individual atoms or ions or molecules, we say. As any material, these ferromagnetic materials also have molecules and ions, and each of these ions possess a dipole moment like in a paramagnetic material. However, they interact with one another. These individual molecules interact with one another in such a way that, where was I? Yes. They spontaneously align themselves. They align themselves spontaneously in a common direction over a macroscopic volume called as domain. This is the confusing point here. Okay, these individual magnetic moments or dipoles, they spontaneously align themselves in a common direction over a macroscopic volume. A large amount of these get aligned in a single direction called as a domain. Okay, these are randomly oriented. Okay, it seems this arrangement of this domain and how this arrangement takes place is not something we need to know right now. Due to this arrangement, and we call this arrangement as a domain, and each domain has a net magnetization. Typical domain size is 1 mm and the domain contains about 10 power 11 atoms. In the first instant, the magnetization varies randomly from domain to domain and there is no bulk magnetization. So basically, magnetism is similar to paramagnetism, but in paramagnetism, where individual atom magnetic moments aligned to give net magnetic moment, but in case of ferromagnets, individual domains, I believe, are the volume unit volume of already aligned atom dipoles get aligned according to the magnetic field direction, so that a substance is magnetized, and is it due to these large amounts of aligned atoms forming domains? The net magnetization of ferromagnetic substances greater than I mean not paramagnetic. Why are ferromagnets permanent magnets? After removing the external magnetic field, some domains stay aligned due to defects, lattice spinning, of hysteresis, or whatever it is. That's why substances like iron, cobalt, and nickel can be made into permanent magnets. Thank you for the bonus. I was about to ask the same question. Anyways, let's go. The individual atoms or ions or molecules in a ferromagnetic material possess a dipole moment as in paramagnetic material. However, they interact with one another in such a way that they spontaneously align themselves in a common direction over a macroscopic volume called as domain. The explanation of this cooperative effect requires quanta. Okay, each domain has a net magnetization. Typical domain size is 1 mm, and the domain contains about 10 power 11 atoms. The first instant, the magnetization varies randomly from domain to domain, and there is no bulk magnetization. That is the first instant where the magnetization varies randomly from domain to domain. This is shown in figure 5.8a, where before magnetic field applied, or at the instant of magnetic field applied, the domains, the bulks will be like this, a random arrangement. But when we apply an external magnetic field, let's assume B naught, the domains orient themselves in the direction of B naught, and simultaneously the domain oriented in the direction of B naught grow in size. This existence of domains and their motion in B naught are not speculation. One may observe this under a microscope after sprinkling a liquid suspension of powdered ferromagnetic substance of sample. This motion of suspension can be observed in figure 5.8b, shows the situation when the domains have aligned and amalgamated to form a single giant domain. Here individual states, here a single country. Thus, in a ferromagnetic, oh, it seems the chapter is over here. There is some summary here. Okay, that's okay too. Thus, in a ferromagnetic material, the field lines are highly concentrated in a non-uniform magnetic field. The sample tends to move toward the region of high field. Let's read that statement. Okay, they're saying in a ferromagnetic material, the field lines are highly concentrated In non-uniform magnetic field, the sample tends to move towards the region of high field. That is, second point is basic. The first, they're saying more like in paramagnetic only, we saw so many magnetic field lines were concentrated, and in ferromagnets, of course, even more concentration of magnetic field lines is seen, and this ferromagnetic substances tend to move from region of high field, like towards the region of high field from low field as its attraction. We may wonder as what happens when the external field is removed. Yes, in some ferromagnet materials, the magnetization actually persists. Such materials, this we saw that was due to some defects in some hysteresis or whatever it was. In some ferromagnetic materials, the magnetization persists. Such materials are called as hard magnetic materials or hard ferromagnets. Alniso or alnico, an alloy of iron, aluminium, nickel, cobalt, and copper, and cobalt and copper is one such material. The naturally occurring iodos, iode stone is another. Such material form permanent magnets to be used among other things as compass needle. On the other hand, before that, let's read that again. And in some magnets, after the magnet external field is removed, the magnetization still persists. These materials are called as hard magnetic materials or hard ferromagnets. Alnico, an alloy. This is alnico. From the name itself, it's an alloy of aluminum, nickel, and cobalt, along with copper as well. And there is also a naturally occurring iode stone. These two are hard ferromagnets. These materials form permanent magnets to be used among others. We can use it as a compass needle. On other hand, there is a class of ferromagnets in which magnetization disappears on removal of the external field, the exact opposite of the persistence. Soft iron is one such material. Appropriately enough, such materials are called soft ferromagnetic materials. Soft iron is a material where it is a ferromagnet, but the magnetization only persists only till there is a magnetic field. After magnetic field is removed, the magnetization is removed. So it is a soft iron, and the material that is called a soft ferromagnetic material. There are number of elements which are ferromagnetic: iron, cobalt, nickel, gadolinium, etc. The relative magnetic permeability is greater than 1000. The ferromagnetic property depends on temperature. At high enough temperature, a ferromagnet becomes a paramagnet. The domain structure disintegrates with temperature. This disappearance of magnetization with temperature is gradual, maybe due to the increase in temperature. This alignment changes, and due to thermal motion, it will become a paramagnet. At high enough temperature, a ferromagnet becomes a paramagnet. Okay, let's see the summary. It was quite an interesting chapter, I guess, at least the last few pages. The summary: the science of magnetism is old. It has been known since ancient times, thousands of years ago. The magnetic materials tend to point in the north and south direction, like magnetic poles repel and unlike ones attract. And cutting a bar magnet into two leads to two smaller magnetic poles cannot be isolated. When a bar magnet of dipole M is placed in a uniform magnetic field B, the force on it is 0. The torque on it is magnetic moment time cross B. Its potential energy is minus m dot B, where we choose a 0 of energy at the orientation where M is perpendicular to B. Consider a magnet of size L and magnetic moment M. at a distance r from its midpoint, where r is greater than L, the magnetic field due to the bar, which is along the axis mu naught m by 2 pi r cube. Along equator, it is mu naught m by 4 pi r cube. Gauss law for magnetism states that net magnetic flux through any closed surface is zero. Consider a material placed in an external magnetic field B naught. The magnetic intensity is defined as B naught by mu naught. B naught by mu naught is defined as the magnetic intensity, the magnetic field per permeability. The magnetization M of the materials is its dipole moment per unit volume. The dipole moment of individual atoms per unit volume is called the magnetization of that property, and it depends on the magnetic intensity, which is magnetization, which is equals to chi times h, where susceptibility or degree of the magnetization with regard to magnetic intensity or due to magnetic intensity, that is n times I. The magnetic field B in the material, the total magnetic field, which is represented as B equals B naught plus B due to the core, where this we will calculate, we will get to it, the B naught, which is equal to mu naught Ni, and Bm, which is equal to, I believe, m times mu naught, and Ni we can take it as h, so m mu naught h mu naught plus m mu naught, which will give the total magnetic field. Mu naught we can take common, and I believe we can write m, which is equals to, yes, chi into h. So chi into h, so h mu naught plus h chi mu naught, h mu naught out, so 1 plus chi h mu naught, which is equals to B net, where h mu naught times mu r, where 1 plus chi is equals to mu r. This is the magnetic field B net. I'll erase this. Where B equals mu naught h plus m for linear material, m which is equals to chi h, so that B equals mu h, and chi is called the magnetic susceptibility of the material. The three quantities chi related to magnetic permeability and magnetic permeability of the material are related as follows. Only one is independent, where all three are dependent, where if we know one, we can find all the other three, where mu equals mu naught r and mu r, which is equals to 1 plus chi. Magnetic materials are broadly classified as dia, para, and ferromagnetic. For diamagnetic materials, chi is negative and small. For paramagnetic materials, it is positive and small. Ferromagnetic materials have a large chi value. Substances which are at room temperature retain their ferromagnetic property for a long period of time are called as hard ferromagnetic materials or permanent magnets. Now there are symbols here: permeability of free space, mu naught, scalar, and so on, magnetic field, magnetic induction, magnetic flux density, all are represented by B. The density of magnetic flux and magnetic induction, magnetic field, all are B, where 10 power 4 Gauss, which is equal to 1 Tesla, and Gauss is the CGS unit of Tesla. Magnetic moment, it's a vector as well. Only magnetic permeability of free space is scalar. Magnetic moment, which is vector. Magnetic flux, which is phi b, scalar. And its unit, it's Weber. Weber, which is Tesla per meter square. I mean, not per meter square, Tesla meter square. Magnetization, capital M, vector, ampere meter per meter, magnetic moment by volume. Now, magnetic intensity, magnetic field strength as well, like electric intensity and electric field strength, where H, which is representation as H, it's a vector, dimensions, so it is same as magnetization, where chi is dimensionless, ampere per meter, where B, which is equal to mu naught H plus M, magnetic susceptibility chi, scalar, no dimensions, so no unit as well, where M equals chi H, the effect of magnetic intensity or magnetic field strength on magnetization, which is given by proportionality constant chi, relative magnetic permeability mu r scalar, which is B mu naught mu r, which is equal to H, magnetic permeability of material, it's scalar as well. It is B equals mu H, where mu is equal to mu naught times mu r. Points to ponder: a satisfactory understanding of magnetic phenomena in terms of moving charges currents was arrived after 1800 AD, but technological exploitation of these directional properties of magnets predates this scientific understanding by 2000 years. Okay, that's saying that a satisfactory understanding of magnetic phenomena in terms of moving charges currents that was arrived in 1800 AD, that is 1820 by Oersted, first discovered that moving charge produces a magnetic field, but technologically exploitation of the directional properties of magnets predates this scientific understanding by 2000 years. Before we knew this current can create magnetic field only, like 2000 years before that itself they exploited this magnets. Thus, scientific understanding is not necessary condition for engineering applications. Ideally, science and engineering go hand in hand, one leading and assisting the other in tandem. Magnetic monopoles do not exist. If you slice a magnet in half, you get two smaller magnets. On the other hand, isolated positive and negative charges exist. There exists a smallest unit charge. For example, the electronic charge with the value of 1.6 × 10 power minus 19. All other charges are integral multiple of this smallest unit charge. In other words, charge is quantized. We do not know why magnetic monopoles do not exist or why electric charge is quantized. Okay, this is mostly information about charge and how we don't know why magnetic monopoles do not exist or why electric charge is quantized. A consequence of the fact that the magnetic monopoles do not exist is that magnetic field lines are continuous and form closed loops. In contrast, the electric field lines of force begin on a positive charge and terminate on a negative charge or fade out at infinity, meaning they go till infinity. A minuscule difference in the value of chi, the magnetic susceptibility, yields radically different behavior, diamagnetic versus paramagnetic, where diamagnetic is positive, like 1, 0 to 1, and diamagnetic is from -1 to 0. Diamagnetic versus paramagnetic. For diamagnetic materials, chi is minus 10 power 5, whereas chi is plus 10 power 5 for paramagnetic materials. There exists a perfect diamagnet namely a superconductor. This is a metal at very low temperatures. In this case, chi which is equals to -1, mu r which is equal to 0, mu which is equal to 0, the external magnetic field is totally expelled. Interestingly, this material is also a perfect conductor. However, there exists no classical theory which ties these two properties together. A, a quantum mechanical theory by Barden, Cooper, and uh, Schrieffer, I believe, BCS theory explains these effects. The BCS theory was proposed in 1957 and was eventually recognized by a Nobel Prize in Physics in 1970. Diamagnetism is universal. It is present in all materials, but it is weak and hard to detect if the substance is para or ferromagnetic. We have classified this might be an important point to be remembered that diamagnetism is universal. It is present in all materials, but it is weak and hard to detect if the substance is para or ferromagnetic. I believe it is para or diamagnetic. Let's verify it. Explain this statement. Explain the statement. When external field, these moments get aligned with the field producing the contribution from, but its opposite in okay, and much smaller magnitude. Para or ferromagnetic behavior. All materials are diamagnetic, but okay, it materials with no unpaired electrons like water or bismuth, diamagnetism is the only magnetic here, so it's visible. In materials with unpaired electrons like iron, nickel, paramagnetic or ferromagnetic, effects dominate, making the diamagnetic part partially in partial, I mean practically invisible in observations. Okay, it is important to remember that diamagnetism is universal. You see it in diamagnet, you see it in paramagnet, you see it in ferromagnets, but it is hard to detect in para or ferromagnetic substances. That's all. It is there, but it is not detected. That's all. We have classified materials as diamagnetic, paramagnetic, and ferromagnetic. However, there exist additional types of magnetic materials such as, it is better if I highlight it, I guess. Diamagnetism is universal, present in all materials. We have classified materials as diamagnetic, paramagnetic, and ferromagnetic. However, there exists additional type of magnetic materials such as ferrimagnetic, antiferromagnetic, spin glass, etc., which are exotic and mysterious. Wow. So with that, I have completed first NCERT revision of chapter Magnetism and Matter completed. See you in